Hey, all right, I'm back, and this is going to be part two of our workshop on creating PCBs, and this is in this instance we are going to actually lay out our PCB. That's the actual PCB design. So we've done the schematic design. That's the logical design. Now we want to do the physical design. And then after this, we'll talk about assembly. So one thing that I want to mention before we get started is that I often find it helpful to sketch out, or you at least want to have kind of an idea generally about how you want your PCB to be laid out before you actually go start laying it out. No plan survives contact with the enemy, but it is good to have some sort of idea to begin with, and it can even be just a quick sketch. This is a sketch that I made on my iPad of another, of our early Core-Compute developer modules, and it's just super helpful to have kind of an idea. And it doesn't have to be complex or anything. Just grab a piece of paper and sketch it out, and that will really help you in this to get started. So let's get to it. So popping back over to our schematic that we created in the first talk, there's a couple things that I want to do. First is that there's a mistake in here, which I realized after I had turned off the recording box. We never hooked up our I2C lines. So we have I2C coming off of our SCD40 CO2 sensor, and we have our pull-ups on the I2C lines, but we never actually hooked them up to the I2C on the Core-Compute module, which would not work so well. So I put a little to-do here, note. So let's fix that real fast. And had I not closed those off with no connect, then it would have given me an error. All right, so here we go. There we go. We got that in. And then I want to do one other thing for cleanup. I want to just name some of these things. Meadow Core-Compute module. And this is going to be our USB-C power boot reset add-on. And then our CO2 sensor. It's going to be our I2C pull-ups. All right, cool. So we got everything. So now we need to convert this into a PCB. So if we go up to design and we do convert schematic to PCB, that will create a PCB for us, or like the initial drawing, and we're just gonna hit OK for there. And all right, so a couple of hygienic things here. I want to first, I want to do a couple of things. One, I hate these lines as the grid style as a line, and it just drives me nuts. So I want to do that. Oh, that's so much better. Second thing is that it creates an outline for me, and I don't want that. I want to create my own outline, so I'm going to delete that. And then finally, one thing I want to do is set up my actual grid. So one thing that you'll notice here is that, so right now it's in units, millimeters, but then the grid size, it's kind of weird. 2.54 millimeters and 0.127. And if that seems kind of familiar, that's because that's basically, if we click this over to mil, then that's the metric equivalent. So I don't know why it assumes that. Historically, PCBs were laid out on an imperial measurement system, which is these mils, and mils is a thousandth of an inch. So 100 mils is 0.1 of an inch, and that's what breadboards are laid out on. That's that grid, and that's like our feather module, that's laid out on, this follows the Adafruit Feather specification, and it's breadboard friendly, so it's laid out on those mills. Unless you're specifically required to do a metric design or you want it to work in a breadboard, I almost never lay it out in imperial measurement. I almost always use metric, and that's kind of, almost everyone has, sort of moved to that. It just makes things so much easier. So I'm in my metric units. I want to change my grid size, and this is sort of, this is a bit of preference, and then also as different designs will lend themselves towards a different grid. But I usually do a millimeter grid with a snap size of 1/4 millimeter, and then an alt snap of 0.1 millimeter, and that works out pretty well for me. So once I've got that, just a real quick intro to the UX here, the designer in design mode, in PCB layout mode. Things are a little bit different. First of all, the design mode has nets over here, and you can turn the visibility on off, which is really nice. Like when you're laying these things out, your power and your ground, getting rid of those right away is really nice, because that simplifies the number of rat lines that are here. And a rat line is these blue lines that show where things should connect logically. And then over here you have layers and objects, so you can navigate around. You can hit T to get to the top, B for bottom, and you'll see over here. And then you've got these different layers that you would draw on. Like when we want to draw the board outline, we would choose that layer. And then another thing that we'll show in a moment is turning on and off a copper area. So we will oftentimes do a copper pour, and being able to turn that on and off is super helpful. And then you've got these other tools up here, which we'll explore as we hit them. Most of the time, we're just going to be doing tracks, labels, maybe some bolt holes, etc. All right, so starting a layout. I actually, I have to say that I really love doing PCB layout. I find that it's very meditative. It's kind of like Sudoku or something. It's a really nice. It's just a really nice exercise. It's like I said, it's very zen for me. But the process is to first kind of get a general sense of your layout by putting you grab your big components and you put them where you want, and then you take your other components, and I'm going to turn off all these rat lines to begin with. And then what is super helpful is first group the components that are related. So as you lay them out, they're already sort of grouped. So what you can do is you can go over here to the schematic view, and we're going to select all three of those components because we know those go together. And then, oops, it didn't. So if we select that and then we go over here, interesting. Usually, when you select a component and then you come over here, the component should still be selected, and I'm not sure why they're not synchronizing. But we need C2 and we need C1, so those two are together. And then if we look at the next group of components, are going to be the RGB LED and then the resistors that go with it. So that's this, and then it is R3, R4, and R5. So R3, R4, and R5. So that's our RGB LED. And then these are our I2C pull-ups, so we're just going to pull them off to the side. And I want kind of a strip of design here. This is like a little, think of this as a little CO2 sensor that you can kind of place around, and I just want something kind of long and skinny. And so what I'm going to do is I'm going to place this USB board at one side, and then I'm going to put the Core-Compute module on the other side, and then I'm going to put this CO2 module. I'm probably going to put it down at the bottom here. And the one thing that I'm thinking about here is that there's a USB line between this USB add-on module and the Core-Compute module, and there you see it, USB D and N and DP. So those are going to connect, and so I just want to be kind of out of the way of those. So we're gonna pull this down and pull this down. All right, and then I'm gonna put the RGB LED somewhere kind of up here, and then that's probably about how I want to lay this out. I want to do a couple things. I'm going to take both of these, and I don't need these prefixes. I know what they are. You know, when the prefix is useful for when you're assembling the PCB, it can tell you what component they are, but this is pretty obvious what they are, and it will just kind of distract and take up space that we don't need. Next thing I want to do is I'm going to add some bolt holes. And this is going to allow me to mount the PCB into an enclosure or onto like a prototyping grid or something. So you got a couple options. You can either put a pad or you can put a hole. If you put a hole, it's literally just a hole through the PCB. But if you put a pad, you get a nice sort of metal, exposed metal on there. And so I generally, for bolt holes, I use pads. And I do that because that way the bolt will have nice something to sort of like, you know, something hard to press against. And this is I'm gonna use this is just a small PCB, so I'm gonna use an M2 bolt on here, which means I need a hole that's a little bit, so M2 is at metric 2 millimeter, so I need a hole that's a little bit bigger than the screw, so it'll clear, and 1/10 of a millimeter is actually plenty. These are pretty high precision. And then if I grab my digital calipers, and I don't have an M2 bolt floating around, but if I measured the head on it, I would get somewhere around 3.5 millimeters. So I'm going to make this pad 3.6, and then now you see you've got a nice metal pad around there. So we're going to get rid of our hole, and then I'm going to put this somewhere here. And it's a good idea. I found that it's a really good idea to lay out your bolts for prototyping, at least on a 5 millimeter grid, because prototype grids are often 5 millimeters. So if you want to, like, you can even 3D print a grid of holes, and then you know, you could mount this to that grid. So if everything's on 5 millimeter, then it'll fit real well. So to do that, what I do is I switch to the document layer, and I'm going to grab my dimension tool, and I'm going to click what would be the center of the hole. It's not on the center right now. And find the nearest 5 millimeter location. So let's get this centered there. All right. And let's make another one up here. Center it there. All right, cool. And then we're going to center this in between these two. And that looks centered, but again, if we wanted to make sure, we can go up and we do 15 millimeters, and then you can see that's the center. Cool. And I'm going to start my board outline, and the first thing I'm going to do is make some arcs to make a round corner. I like nice round PCBs. And let's rotate that so it's correct. Put it here. All right. Center it. Do this one. Hit space to rotate, just as with the schematic designer space. And then grab this one. I don't need a reference point. It's asking for a reference point. So if I want to if I want to copy that and use this as a reference point, I can click that, and you'll see now it's up like that. But if you just hit escape, it'll do a reference point in the center of it. So here we are. Put this one kind of here. Go back to our document, and again, let's get this on a 5mm prototype grid. Let's do 95. There we go. I think we can do that. So move this up in, center it. Looks like we got plenty of room. We can even go smaller if we want. So why don't we make this 90? All right, oops. Cool. Looks like plenty of room. And we'll do our last one. All right. And then one thing, because we were on, because it was originally on Mills, it had the weird values over here. These lines are, if we look at them, the width is 0.254 mil. And I want to make my outlines smaller. I'm going to make them 0.2. And now I'm on, let's go back to the board outline, and let's close this up. And let's make that also 0.2. And now it should remember our value. So I hit W for wire, and we'll close this one up. And we'll close this one up. And on complex designs, usually it takes a little bit more time to get to an outline because you have to do a lot more component placement and figuring things out before you know what it'll fit in. But generally, I like to get an outline in sooner rather than later. We'll save this, and if we hit 2D, this will give us a view of what a quick view of what the board kind of looks like, which is nice. So going back to it. All right, we got that, and now I want to let's go back to our design manager, and we want to orient these components. So I want to show my I²C lines, and I'm going to rotate this so it's relatively easy to route. And I've got a couple of options here. So if I rotate it like this, let's see where our other, so here's our two I²C lines, data and clock. And in this case, we're going to find out that it doesn't really matter which direction it's rotated in, but we'll start this way. We'll just put it close to our Core-Compute module. And then these, as I sort of figure the placement out, then what I do is these are really big, these labels. So I go change this to this. It's on Noto Serif Medium. I usually change it to Demi Light to makes it a lot smaller and gives me more space to do things. And then these two capacitors, recall they have to be next to the power here. So they need to be right next to 19 and 7. Those are the two 3.3 volt leads. So we're going to put this one right here. And what's nice is that because I changed the font here, I always know, like, oh, I've already laid that out. I've already like considered where I want to put that because the label is already changed. So if you look at these other ones, it's clear, oh, I haven't laid those out yet. I haven't laid these out yet. Okay, and then I'm going to put this one. I'm going to put let's grab our I²C resistors. And these are going to be in line. So I'm going to make this one here and this one here. And then we'll rotate. Okay, so I'm pretty happy with that stuff. And now I'm going to show the LED signals. R4, R3, all this stuff. All right. And I'm trying to lay this out so that these are, you know, the signals are easy to route. So you can imagine, okay, this line's going to go here. This one would have to jump over this one, so we can put that up, and then we'll put that one down. There we go. That's nice. So let's now and as we actually route these things, we may adjust again, but this is just to get a good start, get things kind of lined up where we want. Cool. Let me save this. And now we need to start routing. And as we start routing, we basically do the most important, the most constrained signals first. So USB signals, SPI, I2C, any other buses, and then we go to like the simpler signals, like these, PWM signals for the LED, etc. And something to consider here is that USB is an interesting signal. It's a high-speed signal, and it has some constraints around it. And so if we went in and so I hit W to do a wire, and then I just go in and I wire it up like that. That may work. It may work. USB can be pretty forgiving these days, but it is a high-speed signal, and there are things that we need to concern ourselves with. So let me show you the right way to do that. And in order to do that, we need to go back and look at the slides and talk through some things. Okay, so in order to run a USB line the right way and have good signal integrity, we have to worry about something called impedance, and we have to control the impedance. And impedance is an AC characteristic that describes the capacitance, inductance, and resistance at a particular frequency on a line. And this is measured in ohms, but it's not a simple DC resistance. It is a more complex characteristic, and it's something that we have to concern ourselves only when we're doing high-speed design, like in USB or RF radio signals, like doing antenna layout, etc. And we don't actually need to know a lot about this to do good high-quality PCB designs. Really, all we need to know is what is the expected or necessary impedance for a particular signal, and how to control that for our particular PCB stack up. And when I say that, what I mean by a stack up is when you order a PCB, you're actually going to get a multi-layer board that has like copper and then fiberglass, more copper, more fiberglass. And in the boards that we do for controlled impedance, you basically needed a minimum of a 4-layer board, and that is because in order to control the impedance, there has to be a layer on the other side of your signal plane that's fairly close. And in a 4-layer board, that'll be close enough to have some controlling effect on that impedance. On a 2-layer board, that opposite layer is going to just be too far away. Otherwise, you would have to have these massive signal strips. So we do a 4-layer board, and the stack up is basically, okay, what is the distance between each of these layers, and what is the dielectric constant of each of those layers? And you can feed these things into a calculator, and then it'll tell you, okay, given a 90 ohm controlled impedance. This is the size of strips. This is the size of wiring, of traces you need, and this is the spacing, etc. And to do that, you can actually go into, there's a lot of these impedance calculators online. If you Google impedance calculator, you'll find a bunch, and you have to go in and manually enter your dielectric thickness and things like that, and then you can actually it'll actually calculate for you. Now, what I typically use is we order our PCBs, our prototype PCBs from JLC PCB, and they actually have a controlled impedance calculator. So if you go into you go to JLC PCB Home, click on Capabilities, and then there's the stack up information and the impedance calculator. Now, I say that I usually use their calculator, but they just put a new one up, and I've already crashed it. There's a bug in here where it's retaining some information, and so it's not working so well for me. But there is their old one is still up, and you can actually find that by going to cart.jlcpcb.com/impedance calculation, and that this gives you the old calculator, and it's pretty easy to use. And so what we need to do is we need a 90 ohm differential controlled impedance. And to understand the differential thing, let's pop back over to the slides real fast. And USB signal is a signal that's done over a differential pair. And basically what that is they are two complementary signals that run next to each other. So the USB line has this USB D, N, and DP, and that's negative and positive. And what happens is that you have one logic signal on one line, and then they invert that logic signal on the other line. So these lines are always at opposite to each other, and that ensures that they can actually that ensures a higher signal integrity and allows them to go over longer distances. So you'll find these also in Ethernet. That's a differential pair. That's actually 4 pairs of differential pairs, and that allows high-speed transmission without losing that signal. So to calculate this, we go over here and we choose first one, impedance and trace space, and we know that this is a 90 ohm, and it's a 6-layer board, and that's the default thickness, 1.6, and we're going to run these on the outer layer, and then we just need differential. And then the trace space is the space in between the signals, and generally the smaller the better. If you go too big, it actually will say sometimes, hey, we can't even do that on this stack up. But also your traces will get will get very big. So you can start with a smaller one, 4.5 mils. The nice thing about the new calculator actually is that it does metric, so you can put it in. You can start with metric and then instead of doing mils. But again, we'll have to wait for that calculator to get fixed. So what it's saying is that if the trace space is 4.5, then the recommended trace width is 7.54 mils. So we need to go to Google and we say 7.54 mils to mm. And that gives us 0.19. So we're going to go back in here and we'll make a note down here. So we'll controlled impedance. So USB is 90 ohm. And that means that on that particular stack up, so if we go back over to the JLC PCB, the stack up that we're going to use is the JLC 7628. They have different stack ups. And they give you different characteristics. This is the most common stack up, and this stack up's available in black. I don't think the 3313 is available in black yet, so I usually just stick with this one. On some designs, when you have very small traces in order to do controlled impedance, because you're like going through a BGA or like a very tightly packed IC where you have to have you know, it's got little balls on the bottom. That's a BGA is ball grid array. BGA, ball grid array. This is what you see on the bottom of like the MCU, in fact. Then you have to have really tiny traces to fit through there, and then you might need a different one. But in this case, we're going to use this JLC 7628 stack up. So JLC 7628, and we're going to say, and then we'll do, we go back to here, and that's 7.54 mils, so 0.19. So we'll trace width is 0.19 millimeters, and then we need the spacing. And that is going to be, if we go back over here, go back to our calculator, we see that that was 4.5 mils. So we do 4.5, so 0.11, 0.11. Okay, so now we know what those tracing, what the controlled impedance traces have to be. Then we can go back over here, and we're going to go up to our design rules. And in here, this is where we can actually specify those. And while I'm in here, there's a couple things I want to do. There's a conversion bug. If you start in mils, you'll see that the clearance on these is 1.52. The via diameter is 0.61, and this is 0.305. And just to give you an idea where those come from, again, if we go to the capabilities, you'll see that this is the via diameter is 0.6 and drill is 0.3. And then what that comes from is that for a 2-layer board, if we go down to drill hole size, you'll see 0.6 on 0.3 is the hole size on a 2-layer board. Looks like they've and then the via diameter is over here. Now on a 4-layer board, they're actually much smaller. Yeah, multi-layer, they go down to 0.15, and we're going to do a multi-layer board so we can actually make these smaller, but we're not going to worry about it right now because we're not doing any small vias, but we are going to fix these the translation errors. So these should be whole numbers. All right, now we need to add a new rule, and we're going to call this 90 ohm, and the trace width was 0.19, and the clearance was 0.11, and then we just copy these other ones over. And we have to now assign those to these signal lines. So we go to the USB DN and apply it, and USB DP and apply it. So now those are applied. And for the rest of the signals, when we wire them up, we just hit the W button, and then you drag a wire and then hook it up, right? Pretty simple. With this, with the USB line, because recall that it is it's a differential pair, we actually have to run this special, we have to use a special tool that makes them very close, and so they follow each other right next to each other so that the signals are balanced against each other. So we go here and we're going to go tools, or route, differential pair routing, and then we grab one of these lines and then we go to there, and there it is, a differentially routed pair. And it'll also do, like on high-speed signals, where you have a bunch of different signals and they all have to be the same length. The tooling will help you actually make them the same length as well by adding loops and adding curves and things like that. But we don't have to worry about that here. Turn the nets back off. Okay, so that's routed our USB signal, and let's get the nets that we want. So that's the hardest signal to route. Now, next thing that we're going to do is route our next most important signal, which is going to be our I2C bus. So the first thing that I'm going to do is I'm going to route from here to here, and I'm going to just check this signal, this trace width, and it's at 0.2, which is fine. Generally, anything for the PCBs that we do, anything bigger than 0.2 millimeters is generally fine. But I like to do 0.25 or 0.3. That's typical. So I'm going to make this bigger. 0.25, 0.2 you need when you're trying to fit through tight routes and stuff. So I'm just going to go 0.3 on here. Route that. And now I need to do something. I need to get this signal over to here and this one over to here, and it's got to go, it can't go through the top because there's stuff in the way. So I want to route it underneath. And I am going to route it in the next layer down. And so to do that, the first thing that I have to do is I have to put a via. And there's a little trick. If I put a via out here, it doesn't have a net name. So it's just any random via. But if I put a via, by the way, to get to a via, you can either hit this the via tool up here, or you hit V. If I put it on a named part, then it'll grab that part name. So that really helps. All right, so I'm gonna run these to these vias, and vias are like little tunnels. They go through the board, and vias are free, by the way, on your when you're making a PCB. So don't feel like you need to skimp on vias. So I'm gonna put via there, and then I'm gonna put 2 more vias here. And there's another little trick. If I put it right in the middle, when I move it out, it's gonna grab that line. But if I put the via just on the corner, it doesn't grab that line, but it does grab the name. So here we are. Boop, 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 boop. And now I want to go to a layer below, so I have to first add more layers. So I can go to Layer Manager. I'm gonna make this a 4-layer board, and they are signal or plane. You're almost always going to do signal, even if they're just a plane, which we'll talk about when we pour them. You get a lot more control over making signals. So you still have your top layer and your bottom layer, but now you also have these inner 1 and inner 2. So I'm going to put this on the inner 1 layer, and you can toggle between these by hitting 1 or 2. So T for top, B for bottom, 1 for inner 1, and 2 for inner 2. And I'm going to pull this up, and we'll have real nice straight signals. Not necessary, but kind of a nice little trick. Okay, so those are routed. And now I want to route the rest of my board. So let's turn all the nets on and then turn off power and ground. And if I refresh this, you can actually see a number of these have already been routed. So let's go back here, hit T for top, and then let's route these signals. And notice this is the wrong size, so we're going to resize it up. And this one probably won't fit in there. See that? It won't fit. So what I'll do is we're just going to drag and make some clearance for that signal line. All right, so those are in. Here's our LED. All right, very good. And while I'm in here, so I got a couple more things to route. But one thing that I want to do is with this controlled impedance line, with this USB, you'll notice that on either side is a ground lead on both ones. There's ground here as well. So I'm gonna do a copper pour, And that's up here, that's this dotted line area thing. And I'm going to choose ground. And what I'm going to do is, oops, let's try this again. I'm gonna basically wrap this whole area in a ground copper core to catch stray signals. And again, this is really just this is really the kind of the extent of the complexity that you'll deal with on a core compute powered PCB. Is just this the USB signal. And then while I'm here, later on I'm going to add more ground planes underneath. So I'm going to put some ground vias here. All right, and then we're going to do the same thing over here. And as I do this, it's left click to define the area, and then when the last one, I right click to close. All right, let's get that up in there. Cool, so that's looking good. And now let's route these other ones. So we're gonna put a via here, and a via here, and then drag them out. Wire them up. Cool. And then I put these on inner layer 2 because they're going to cross underneath this, and I need to make sure that underneath this is a ground signal, not a control signal, because they can interfere. So I'm going to be, this is inner layer 2, and again, if we went to our tools layer manager, you'll see top layer, inner layer 1, inner layer 2, bottom layer. So we're going to go below that copper underneath the USB and then to the next one. So we're inner 2, and I'm going to run this. And you'll also notice that allows me to cross under these I2C lines on that one. On this one, I am going to run behind. Oh, that's the wrong one. This one. Oh, and we'll do this. This is a nice trick, is that you just pull them up to where you need them, and then you have less crossover. Okay, and then this one, last one. I've got a couple options here. I could actually drag these forward like this, and then I could go behind them. Or I could route all the way behind. In this case, I'm just going to do this. This is pretty good. Again, these are on layer inner 2, not layer inner 1. Okay, so this is looking good. We're effectively almost done. The next thing I got to do is I got to get power and ground everywhere. You notice that all of these here are ground, all of these are ground, and then there's some power signal, and there's a bunch of ground here. So what I'm going to do is we'll refresh this. We'll notice that there's only 2 left. So I am going to come out here, and I'm going to do some ground vias. And then instead of wiring each one of these like that, what I'm going to do is, it's just really nice to have a good solid ground connection. I'm going to make a ground pour here. There we go. And then over here, we're going to do some vias, some ground vias. And this is kind of overkill, but it is nice to have just a real solid return path for power. Do the same thing up here. All right. Great. And now I want to do some copper pours on each layer for power and ground. And generally the way that you do this is that you always want ground on the opposite side of your components. So a typical stack up would be power, ground layer, power, ground layer. So we're going to pour on top power layer 3V 3, and I start outside of the outside. That way, when if I have to select this later, I'm not competing with selecting like the board outline. All right, so there's the top layer. That gives 3V 3. And notice that a lot of rat lines went away for all the power because the power is all now wired up as well. And if you were continuing to route in here, something that's really helpful is being able to turn off the copper area. So you can toggle the visibility over here on the layers and objects. All right, now I'm going to go to the inner one layer and we're going to pour a ground plane. And inner layer 2, back to power. And then finally, on the bottom layer, we're going to back to ground. All right, very good. So now cycling through this, top, inner 1, inner 2, and then bottom. So now we need to start actually tying these things together. So we have, well, let's go through and let's get all the rest of our grounds wired in. So I'm going to turn off the copper area so I can see that I'm not putting a via through a line. So here's a ground down here. And this is an antenna grounding. So I like to put lots of stuff here. And again, this is a place where we can actually pour a ground layer. And something interesting about this, if we show the copper area, and then you hit Shift B, which will rebuild the copper area. Something's interesting. There's no copper pour there like there is here. And it's because the order of operations affects order of these of where these are drawn affects whether or not they get drawn. So the workaround there is that we pull off the big one. So hit cut, grab a place, and then if you rebuild, you'll see it'll show back up, or it'll show up now, and then we can just re-add that top one, and then it gets drawn last. So now we have this really nice ground plane there, and then turn it off again, and go wire up some more grounds. And with these power filtering capacitors, you know, you might think that it'd be enough to just do like that. Like, it is ultimately connected to ground, but it's always good to give them their own via. There's some weird thing that can happen if you don't individually connect each capacitor, power filtering capacitor to ground. Okay, so it looks like I think we got basically everything routed. We hit Shift B to rebuild. We'll save. And now let's go refresh that. Looks like everything's routed. So that's good. And we've poured all of our planes. So this is looking pretty good, actually. The final thing that we want to do is we want to kind of stitch these planes together. So the ground layers are really well connected. Like, near every ground thing, there's vias connecting the planes. But the power plane, the 3V3 power plane, is actually only connected on top because we haven't sent any vias through to the other planes. So what we're going to do is basically wherever power is needed, we're going to make sure that it's got good connection to the power planes. So I'm going to do some vias near anywhere that we need power. And if you actually hover over a 3V3 lead, you know, one of the pad or whatever, you actually see all the 3V3 places. So it's kind of a nice, helpful. So there's a good via there, gives us all that. Do one here, over here. All right, I think that might be everything. Oh, let's put one here. Yeah, looks good. And just to clear up some OCD, we don't need two there. So that's good. Let's show our copper area, and now let's rebuild. Great. So our board's basically done. The last thing that we want to do here is provide some labeling, provide some documentation. So I'm going to grab a text field. That's on the wrong. I don't want it on the copper layer. I want it on the silk layer. Silk screen layer is where the printing goes. So I am going to put the label here. We're going to call this our CO2 sensor. And I don't like that font, so you can add your own fonts. You can add true type fonts. So I've got this Wavehouse font in here, which is a little nicer. I'm going to make that a little bigger. Let's make it 3mm tall. And we'll call this like Dev Camp 2023 CO2 sensor. And then the other thing we need is a version. So this is really important. Always put a version on your design so you know what you're looking at. It's very important. Okay, so we got our documentation on there. And now let's go look at this thing. Let's see what this is going to look like when it's done. So we hit 2D view. Look at that. It's a beautiful board. And if we had 3D models of everything, we would actually see 3D parts for... And we had everything but the USB bit and the Core-Compute module. So we have models of these, so I should just add them to EasyEDA, and then you'll see actually the whole thing. But that's it. That's our board. Looks pretty good, right? It was pretty easy to do. So next up, I want to talk about. Let's go back to our slides, and just a real quick process review. So when you're laying out PCBs, and we did this. This is the order of things. First, grab your components and group them up into their logical groupings. Do your rough layout and then size your board, and then route your most important signals first, starting with your high-speed signals like USB, and then your buses like SPI, I2C, etc. And then route other signals, and then do the copper pores, and then add vias to stitch them together, and then, of course, label and document your board. And it's very important, put the version on there, right? So when you get this thing, you know what you're looking at. Okay, so your board's done, but there's one final thing that you want to do, which is to check your design rule constraints. So if you go into the design manager and you go to DRC errors and you click this refresh button, you'll see that there's none. But let's say we've got an error. Let's say we didn't notice this line and we crossed them over. Then when we refresh this, it's going to actually say, hey, look, there's a clearance error. There's like the copper area because we didn't rebuild, etc. And so we've got to go in and fix these. And what happens is that you click on one of these and it shows you the two things and it actually selects them. And so your instinct is, okay, I'm going to grab this and start going. And that time it worked, but oftentimes because two things are selected, you actually go and it does that. So that's not good. So you grab your thing, click your thing, hit escape. So you unselect, and then you can move things around, and then we're going to rebuild our copper area, and then check our DRC errors, and there's none. And so now the board is actually done. All right, so now we save the board. And it's time to order this to fabrication. So there's a couple of things that we need to cover. So the first thing is that in order to fabricate a board, you need to output Gerbers. And Gerbers are the drawing files that board fabrication houses understand. And they can build a board from Gerber files. And if you want to view Gerbers after you've output them, KiCad has this Gerber viewer built in. So if you install KiCad, you can actually check out the Gerbers. You rarely need to take a look at them, but if you do, that's a way to do it. And then, to order PCBs, there's a lot of different board houses. There's piles of board houses out there. For almost all prototype boards, we order from JLC PCB, which is a Shenzhen-based board fabricator, and it's fantastic for simple boards. Actually, it's really fantastic for for complex boards as well. They just do so much volume that they're able to turn around very quickly, and they've got a lot of great options and stuff. The only drawback excuse me, to JLC PCB is that it takes a while to ship. So we always ship DHL, and it's a little expensive. You can also use OSH Park, which is a US-based board manufacturer started by SparkFun. They are considerably more expensive than JLC PCB and have a much longer turnaround time. So because of that, I don't generally use them. Also, the boards are purple. and I don't really love purple boards. But in any case, if you need to order from a US a quick turn house, Osh Park's great. And if you are doing you need very high quality boards. Rush PCB is out of San Jose and also Toronto, and they make very good boards, and they will make it to your specification. And then as you go to volume quantities, there's piles of high quality volume board manufacturers out there. And if you get there, feel free to ping us, and we'll give you some recommendations. So to order, when you do order, there's three things. You need your Gerbers, and then we want to use ENIG, and we want to get a stencil. And so let me talk about that. So when we to order, while we've got our PCB open, if we go up to fabrication, click PCB fabrication file Gerber, and you can have an option whether to check your design rule constraints or not. Always a good idea to do that. And you can either generate the Gerber and download it, and that will give you a file locally, a zip file of all those drawings, and you can send them off to your board house, or you can order straight to JLC PCB. So if we do this one-click order JLC PCB, it pulls up a browser, and it will automatically, usually it automatically automatically adds the Gerber files. Let's try it again. There they are. So this time it's uploading them. And there's a lot of options in here, but we don't really need to worry about most of these options. The few options that I typically care about, so there's the quantity. I honestly always order a minimum of 10. Sometimes when you're assembling or something, 5 just isn't quite enough. Maybe screw some up, especially when you're beginning. And the price difference between 5 and 10 is negligible. So what's it? It's $14.50 versus $8.50. So very affordable. The next thing is their PCB color. So this is the solder mask. So depending on what color you want your board, they've got a lot of different options: purple, blue, green. Green's actually nice because you can see the traces. So if you're debugging, sometimes that's nice. I almost always order black. White's pretty nice too, actually. It does take a little bit more time to do black. And then the other thing is the surface finish. And there's Hassel with lead, lead-free Hassel, and ENIG. And Hassel is hot air solder leveling, and I rarely use Hassel. We almost always use ENIG. ENIG is electrolytic nickel immersion gold. It's basically, the difference between these is one has with Hassel, they put the solder on you on the board for you already, and they do it via hot air knives. They basically use hot air and blow solder across the board. And ENIG is what we use. That's like, if you look at your Meadow board, you'll see that these things are gold colored. Electroless nickel, that's what it is. We use ENIG for everything, and the reason why is that some folks say that Hassel is a little bit easier to solder on, but for assembly, but we found the exact opposite to be true. ENIG is much easier to assemble. And here they say lead free, but sometimes you'll see, or with lead and lead free, sometimes you'll see ROHS, ROHS, and that's Restriction of Hazardous Substances Directive, and that's like lead free, halogen free, etc. And that's a good thing to not have in there, obviously. As you're working with this, you don't want to pick up nasty stuff. And the other thing here is, so I do ENIG, and then it says, hey, listen, if you want to do ENIG, it's going to take a little bit longer if you're do it in black, and I don't care. If it's another 2 more days, I still want black. And then impedance control, you're going to say yes, and this is where we choose our stack up. Now remember, when we were doing the impedance control calculations, they were based on a particular stack up. So we choose the stack up that has the correct impedance control. And again, it's going to say, hey, listen, you know, unless you do green, it's going to take longer. I don't care. So that's mainly, that's the main consideration. If you have castellated holes, like on the edge, again, on the edge of your F7 board, you'll see these castellations. If you have those on your board, then you'll want to say yes, and it'll ask you how many sides. Otherwise, if you don't, they're going to come back a mess. So you want to do that. This, with JLC PCB, I just realized it wasn't showing my screen, so let's go back here. So again, here's the ENIG. No thanks. It's okay if it takes longer. Impedance control, yes, and then it gives you the options for the layer stack up. Choose your layer stack up. And castellation, yes. Number of edges, we don't have it on that. Now, there's also an option to give them for them to assemble this. And if all of your parts are available in LCSC, then maybe you can do this. I've never spun a design. I've hundreds of designs. I've never spun a design yet that can be assembled by them, so I don't bother with that. But the thing that you do want, and this is very important, is order a stencil with this, and it's only $7 for this stencil, and you want to get it for assembling at home. You want to get frameless, so no framework. Framework puts a frame around the stencil, and that's for auto stencil machines that's put the paste on. The stencil basically is a metal sheet that has holes where all the solder would go, and so you buy some solder paste, and we're going to cover this in the assembly talk, and you just smear it through that stencil, and then you pull the stencil up, and it's perfect, and it's ready to put the components on. So definitely get stencil. And then stencil side, this is whether you want just the top, the bottom, or both sides of the board to have a stencil. On most of our boards are just top only, so we just do top, and then they don't even bother with anything else. So there it is, and that's $55 to get a high quality, multi-layer impedance controlled PCB ordered to your door within a week or two. So that's it for this particular talk. Thanks for tuning in on this one. I hope that you saw how easy it is to lay out a PCB and really, again, demystify these complex concepts around controlled impedance and the routing around USB, etc. In the next talk, we're going to take this board that we get back from JLC PCB, and we're actually going to assemble it. And I'll show you how easy it is to do that with very limited equipment in an at-home lab setting. So I will see you in the next one. Thanks.